So in this particular class, we're going to talk about a couple of failure theories. When we do fatigue analysis, there are two things we have to keep in mind. The first thing we want to know is what is the remaining life of a structure? What is how much life it's going to have? The second element that we want to know is if my structure that I'm going to design for the cyclic loading, I actually going to hold it. So I'm not sure if you have thought about this, but many times when you buy something and they give you 1 year warranty, it just happens to fail like a month or two just after the warranty expires, right? They give you a 10-year warranty and then it's going to start failing just after the 10-year. And there's a reason behind the car industry can give you a warranty on a certain part, so for 100,000 miles and 10 years, because they designed it for that. Otherwise, they will lose money for that, right? There is a lot of philosophy embedded in how you would design planes. There are planes, um, the Navy, for instance, when designs a plane, they want to design a plane that will last them, as for an example, 20 years. After 20 years, just dump it. We don't care. But the Air Force likes to wants a plane that can last you as long as they can possibly last. So they will go through lots of repairs to make sure that uh, lots of repairs to make sure that they get a maximum out of that fleet. And that is there's lots of studies and lots of testing and done especially for the fatigue aspect of it. Fatigue is the backbone of structural design because everything actually goes to cyclic loading. Okay, so there are two events. The first one, if it's safe, that's first event. The second event is how much life I have left. It can be infinite life. Infinite life is really relative, right? Like for instance, I can have a plane that's designed for 30 years. Okay, the whole plane, the whole structure is for 30 years. However, the landing gear itself, I don't want to design it for 30. I can design it for maybe 40. Why? That would be my infinite life because the life of the structure is 30 and I'm adding some more to that. But that landing gear will never see the life. So many times the infinite life is a bogus term. It's not like can be used for generations to generations. It just has it surpasses the life of the whole structure itself, so that part will no longer be useful. That's the whole idea behind that. So let's see some of the theories and let's see what we actually want to talk in this discussion. To start this discussion, what I would like to do is I would like to lay out here what we really want to do in fatigue assessment. Okay, let me change this color. So a typical fatigue assessment involves two things. First is going to involve in how much life I have left. Okay. The second question he wants to answer is the structure safe? They're two separate questions and they're actually answered in parallel. So here, not getting a little bit ahead of myself here, that will be the topic of next class. You have an SN diagram. Okay, the SN diagram is nothing else than a diagram in where this is the life of your structure and represents life, as this is your alternate stresses here. And your typical diagram may look something like this for a ferrous material, where and for a non-ferrous material looks something like this. And this point right here, we call this point a knee, endurance limit. And we will talk about that limit as we move along. And this is a log plot, by the way. Okay, and this comes last with testing, test data. This is how we come up with the SN diagram. And the only thing this tells me is the life. Remember, this is life, this is stress. So if I know an alternate stress, I can find I can find what my life or my structure is. Now, on this side, we talk about several theories, and we have something what we call the fatigue safety factor. This fatigue safety factor, it works very different factor of safety. It works very different from the other, fatigue factor of safety, and works very different from the other factors of safety we had talked about. In this particular case, if my fatigue factor of safety is actually bigger than 1, all he's saying is I have infinite life. My n is infinite. If he says that n is less than 1, all he's saying is equal to 1, he says that my life is actually infinite as well. However, if my life is less than 1, I'm saying my n is finite. It has finite life. It could be the case where I is not acceptable as well. Okay, but this is very different, right? Before, when we talked about the structure, we said if it is less than 1, it failed. Now we cannot necessarily say it's failed. We know it's finite. It may not be acceptable, but that would determine by the theory, and we're going to see that in the next couple of charts. Okay, so as we move on, what we have is, these are nice pictures from your book, especially. And what we have here is from test. And just note that this is your SM, and this is your SA, sigma alternate, and sigma mean. We plot this. This is the horizontal line is the mean stress. The vertical line is the alternate stress. Okay, and we call this SA, your book calls it sigma A, but it's all the same. So as you can see here, this is your endurance limit, and just how you calculate this, we'll get to that in the next class. But anything below this is N is actually infinite life. Anything above this, N is finite. Okay, the life of the structure is finite. And you can see there's lots of test data that involves all this. And we have several, this line that you see here, this is the Gerber line. And this line is very useful, especially when we work with, and we will use this when we work with springs and fasteners. Fastener design. Goodman theory is the most typically used theory, and this is the one that we really like. And it's easy to use, it's simple, it's not that conservative, and is quite acceptable with the test data as well. This is a load line, and to draw the load line, I call this RS. Your book calls it small r. It's all the same. It will be sigma A divided by sigma M. Okay, so this is how these plots actually, how they are drawn. And so you can have not only one theory, but you can have several theories. From these theories, the one that I'm going to emphasize more is this one, Goodman. And you can see that this is your ultimate, right? This is your endurance limit, SE. This is your yield strength, yield strength. And don't forget that this is all plot. This is M, and this is alternate. Okay, and so in this particular plot, this is Soderbergh. You can see that's very conservative. This is the most conservative theory that you're going to have, because it goes from yield line to your endurance limit. And but then, you know, anything besides this, it says has a finite life. Anything inside here, you're saying you have infinite life. Okay. So we come to this chart. There are a couple of things that we keep in mind. The first theory I want to go over is the Gerber theory. This is mainly parabolic. We are talking about this particular curve is the parabolic. This one right here. Okay. But what you have to keep in mind when you do this analysis, if it's a yield material, right? It's a ductile material that's going to yield. This may be the curve, but you cannot go beyond this line here, okay? And because you cannot fail because of yielding. And one of the things that we do in our analysis is, but we will get to that later. What we want to do in your analysis to make sure that sigma maximum is actually, as we discussed in the last lecture, sigma A has to be actually bigger or equal, I'm sorry, smaller or equal than sigma yield. This is important, okay? It has to be that so it can stay inside this curve. That's what you want to ensure, you want to make sure. Anything inside this region, so anything, let's say from here, anything inside here, this is infinite life. Infinite n, and your factor of safety here would be bigger than 1. Anything outside this line, let's say here in this region, your factor of safety will be less than 1, and the life is finite. Okay? Anything outside here, this is, let me change the colors. Anything outside here, this is not acceptable. Okay, we want to stay within the bounds of this. This, what you see right here, this is how you calculate the factor, the fatigue factor safety for Gerber. This is the equation. The other variations of this equation that's commonly used, as you can see that this is R, right? So R is equal to SA divided by SM. So many times this is also written by divided by R. Another thing that, just going back to this equation, this is the Goodman line. This is the one that we always recommend. And if nothing else is given and told you, just use the Goodman line for your analysis. And your fatigue factor of safety is actually 1 over sigma A divided by sigma E plus sigma M divided by sigma UT. Okay? So the other thing that you have to keep in mind, let's suppose I was working in a case of pure shear, right? If I'm working in the case of pure shear, just so pure torsion, let's say, because shear really doesn't enter in fatigue, pure torsion. Then in that particular case, you have your SM, this is actually SA, but this will be actually tau A because it's pure shear, only have a shear, right? So in that case, when you plot your diagram here, you want to use SSU. SSU is and has been shown this is 6-7 times your ultimate tensile. And instead of using sigma y, we're going to use sigma ys. In this particular case, it will be sigma y tensile divided by 3. So your plot will actually look a little bit different. So it's also SE is SE. Okay, so your plot is actually, let me see if I can draw a straight line here. Okay, so this line goes between your SE and your SSU. And this is, again, this is SYS. This is for only the case of pure torsion. And we're going to use this plot a lot later. And you can see that instead of going all the way down there, I have to come down with my yield line that actually does this. Because I want to make sure there's safety, right? So anything outside this region is not acceptable. Anything inside this region is acceptable. Okay, so this is just to clarify how we actually model this, in fatigue. So let's move on here, and let's suppose I have a point right here, right? This point that's outside this region is not good, okay? And this plot is done for mainly for the yield using Goodman, okay? This plot right here, this is factors. Note that they have an absolute value. We have an absolute value here. This is the yield line, okay? You want to make sure that you always check against yield. And as you can see down here, right, I am using S max, and it's SA plus the absolute value of SM. This is what we are actually using here down here. We want to make sure this is actually less or equal than this. So you want to do that yield check as well. And the yield, that's a static yield check, okay? And you want to ensure that yield check is actually bigger or equal than 1. This is not the fatigue, this is yield, okay? Then in this case here, if I have a fatigue and the fatigue is bigger than 1, anything on the line, my fatigue stress is equal to 1. Anything here, my fatigue is less than 1. Outside here, also my fatigue factor safety is less than 1, but this is not good. And here, this is, as you can see, is finite life. It goes from 1 cycle to infinite cycles. This is infinite life. Okay, so that's important. And if you were working with, for the case of pure torsion, right? Let me write this down here. For the case for pure torsion, then again, this would be, you will use sigma ys, obviously, and you have sigma max, right? And it will be bigger or equal than 1. Let me just show you several cases here that I think is interesting to study. These plots are given in your, I am only doing the positive side, but note that all this actually, expands to all this side here as well. Okay, just for the sake of this discussion, I'm going to keep myself on the positive side. So what this diagram is typically for a ductile material, because it goes in from your endurance limit to all the way to ultimate. And this is actually equal to 1. And so if I told you, I gave you a point right here, and I ask you what is the fatigue factor safety, you know that fatigue factor safety will be less than 1. Okay, this is not the acceptable region. If I ask you what is the factor of safety anywhere inside this line, right here, right above this line, okay, you have to know that my fatigue factor safety is actually less than 1. Here, my fatigue factor safety will be bigger than 1. Here, at the line itself will be equal to 1. That is just saying is, this is all infinite life, okay? Anything inside on here is infinite life. And I cannot actually, this is my line. I cannot have anything on this side. That's not acceptable. Okay, so this is a summary of what I just told you. Okay, for ductile material, this is finite life. This is infinite life, and I don't like a point on this side here. And just don't forget, this is mean, this is alternate stresses. Okay, for brittle materials now, on the other hand, what we're going to have for the brittle material, and again, I'm going to focus mainly the attention here. We don't have yield, okay? So I just drew the line to show you, but we don't use yield. We don't have yield at all. We only use ultimate. And don't forget for torsion, this is actually equal to 0.67 times the ultimate tensile. Only pure torsion. Let me write it down here. I'm repeating myself, I know, torsion. Okay, so what you want to do here, this is all, again, anything above this line, this is finite life. Your fatigue factor safety is 1. This is not the acceptable region. This is actually acceptable. This is infinite life down here. And this is what your diagram actually looks like, infinite life and finite life. This is not the acceptable region. Okay, so let's see what happens for several case studies here. Uh, let's see what happens if my fatigue, my factor safety here, for fatigue factor safety of point A, this has to be bigger than 1. As you can see, it's infinite life. If I ask you what is the factor safety of B, you know this is 1, and this is infinite life. So N is actually infinite here. Okay. Now, if I say, what is my C, my point C here, okay, it would be less than 1. My life is finite, okay, finite life. If I say my point D, this is also less than 1, and my life is finite, okay? But my point E and F, they are also less than 1, but not good, okay? I don't want to stay inside that region. I don't want to stay outside this region. And this is the case of no preload, that you start from 0. Now, when you work, especially for springs and fasteners, we will have preloads where you start right there. Since we will have preloads, then your R is actually modified by this equation right here. So you have the SI. And actually, analysis and discussion is identically the same. The only thing that we are changing is we are starting at a different location. We are not starting at 0. Um, and then if you had again, this is the same analysis, right? Even for brittle materials, this point will be positive, bigger than 1. This point will be equal to 1. These 3 points will be less than 1. This will be less than 1, but this is the only not acceptable point. Okay, the other points are completely acceptable. And the same thing if it was, you can have for the brittle case where you have a preload, you're going to start here, but the same discussion applies as before. Um, so I highly recommend that you read your textbook, especially chapter 6. It gives a very good discussion on this.